Okay, we're on to question 19. So this question kind of pulls together a lot of the different parts of the circuit that we built earlier in the module. So what you're asked to calculate in this case is the output voltage, which in this case is labeled V5, right? But there's really three separate kind of blocks here in the circuit. So there's this part here, which is the reference voltage generation, and you can see that it's really just a voltage divider feeding into a unity gain buffer, and that's giving us a buffered reference voltage here, which kind of sets the ground level for the other two parts of the circuit. You've got the 2 op amp in amp here, similar to the previous few questions, and then you've got a non-inverting op amp here, similar to questions earlier in the quiz. So I'm going to work through the three different parts here in order to finally calculate what V5 is here. The inputs to the circuit, the differential voltage input is V2 and V1 here. So we're told the values of V2 and V1. You can see they're very close together actually, and that's because the combination of this part of the circuit and this part of the circuit is going to result in a higher gain than we've seen for the earlier questions in the quiz. So let's look at the reference voltage first. You can see you've got a 5-volt supply here, so it's tied to ground at this point here, so 0 volts at the bottom, and these resistors are both 10k resistors, so we know that this is going to give us half of the 5-volt voltage, so this here will be 2.5 volts. Because we've got a unity gain buffer here, this voltage here is also going to be 2.5 volts, so this is Vref, 2.5 volts. So this serves as kind of like the base voltage for the in amp here, and we can also see that we've got these perfectly matched resistors, or 1 and or 2 here, and the values of these are 5k and 100k. So the gain of this part of the circuit here, what will I call this? A diff is equal to R1 plus R2 over R2. So this is going to be 5 plus 100 over 5, which is 21. So the differential gain of this part here is 21. And then there's also the gain of this second part of the circuit here. So the output of our in amp then goes into this non-inverting amplifier here. So the gain of that part there is, what will I call that? I'll just call it A. So A is equal to, it's going to be R3 plus R4 over R3. So that is equal to 1k plus 10k over 1k. So it's 1 plus 10 over 1, which is 11. So we basically know the gain of this part here, that's the differential gain, and we know the gain of the non-inverting op amp part here as well. And they're both referenced to Vref here. So it's actually quite straightforward to put these together now. We can just say that the output voltage V5 is going to be equal to the reference voltage plus, and then it's going to be the differential input voltage, which is V2 minus V1, multiplied by the differential gain of this part here, which is A diff, but then also multiplied by the gain of the second part here, which is A. So this is going to be equal to Vref, which is 2.5, so we calculated that down here, plus V2 minus V1 multiplied by 21 multiplied by 11. Now I'm going to go to Octave to do this, just in case I make a mess of subtracting V2 or subtracting V1 from V2. So V5 is going to be 2.5 plus let's just move this window over here. V2 is 2.5028 minus 2.4995 multiplied by 21 multiplied by 11. 3.2623. So this is V5, our output voltage. And that's what you're asked to calculate. .2623. And that's it for question 19. So that's kind of like the toughest question, I think, of all of the circuit questions, in that it just pulls together all of the different parts. But this is also like very, very close to what we built on the breadboard. So understanding this is like, you know, really one of the key things I think to take away from the whole module is just to figure out how this voltage here is related to these two input voltages here. Okay, the final question in the quiz is just the resolution of the analog to digital converter. So we covered this early in the module, this idea of what an analog to digital converter does. So it's taking an analog voltage measurement and converting it into a number. So that's what we mean when we talk about digitizing a signal. And you might remember I showed you some examples of converting decimal numbers into binary numbers, and what were the maximum and minimum numbers that you could encode as a binary number with a certain amount of digits. So in particular, if I have an 8-bit binary number, the smallest 8-bit binary number would just be 8 zeros, which is just 0 in decimal. So this is a binary number, this is a decimal number here. The biggest 8-bit binary number I could have is just all ones. And what that would be equal to is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which is 255. Now, of course, 255 is equal to 256 minus 1, which is 2 to the power of 8 minus 1. So there are basically 2 to the power of 8 different 8-bit numbers, i.e. 256 different numbers that we can pack into an 8-bit binary number. So if I've got an 8-bit analog to digital converter, every time it measures its input, its analog input voltage, it's going to convert it into one of those 256 different numbers that could be encoded as an 8-bit number. So there's only 256 different values that you can get out of this ADC. We're also told that the input voltage range is 6 volts, and it's a linear 8-bit analog to digital converter. So that means that all 256 different digital levels are spaced evenly throughout that 6 volts there. So one digital unit is equivalent to that 6 volts range. Now I'm actually going to write this as 6,000 millivolts divided by 256, which is the number of different levels that we have. So that's like 2 to the power of 8, because it's an 8-bit A to D converter. So this will tell me how many millivolts each digital unit represents. So I can go to octave here to do this. So 6,000 millivolts divided by 256 different digital levels is 23.438 millivolts. So that is it. 23.438. Now let's see how I scored on the quiz. Hopefully I've done well there. Submit the quiz. Yes, please. And at least on the practice quiz, you should see a review of all your answers and whether you got them right or wrong. Looks like I'm doing well here so far. Yeah, 20 out of 20. Fair play to me. I've done it again. 100% on my own quiz. So that's it. If you have any problems with any of those questions or if anything isn't clear, send us an email and I'll do my best to clarify anything that's confusing, or if you spot any errors or corrections, please let me know as well. Thanks very much.